Okay, so let's look at what we've got going on here. So it says most vaccines protect only against pathogens that fall within a certain region of antigenetic, okay, sure, space. So the vaccine protects against any strain falling within a sphere radius 2 centered at the point 2, 1, 0. So our sphere is centered at 2, 1, 0 with a radius of 2. Determine determine what vaccine does that? I can't quite remember that. Determine, what's that? Where, when, whether, I don't know. Determine if the vaccine is going to be effective. So basically, they're just asking which of these points is within the sphere of radius 2 centered at the point 1, 2, 1, 0. And there's a couple ways you could do this. Is there a couple ways you could do this? I'm curious though. Probably the easiest way to do it is just to find the distance between each point and the center. So like, is this point going to be in that? Well, let's find out. So for A, the distance between 0, 0, 0 and the center of the sphere is going to be the square root of 2 minus 0 squared plus 1 minus 0 squared plus 0 minus 0 squared, which is going to be the square root of 4 plus 1 plus 0. And that's bigger than 2. So no, that point is not that whatever the virus or the strain at that point is going to be is not going to be covered by this vaccine. So no, our distance is too big. Let's look at the next one. I don't think we need to do all of these though. So for the next one, the distance would be the square root of, again, I'm just taking the distance from this point to that point. So 2 minus 1 squared plus 1 minus 0 squared plus 0 minus 3 squared. And that's going to be the square root of 1 plus 1 plus 9. That's also too big. That's the square root of 11. Also no. What about the next? Let's at least get one word. I think the next one's going to be a yes. So for the next one, the distance between those 2 points is going to be 2 minus 1 squared plus 1 minus 0 squared plus 0 minus 1 squared, which looks like it's going to be the square root of 1 plus 1 plus 1, which is less than 2. So yes. Yeah. That's kind of it. I will point out there's a slightly different question that Grant goes over on one of his handouts here, which let me take a look at it real quick here. It's another question about antigenic or genetic. I don't know. He writes antigenic here, not antigenetic. Antigenic cartography. So this handout's on Grant's 17B webpage, and it kind of it's a similar problem, but talking about how like a vaccine can cover more than 1 year's worth of virus. And talking about finding like the distance between the centers of the spheres. It's worth looking at if you're interested. Or that problem. I think it's so this is problem 8, problem number 30. I can't read that from here. Problem number 39 from section 8.1. So if that problem is of interest to you. Grant has a lot. So if you're not looking at Grant's webpage, you're missing out. If you're looking at Grant's webpage, there's lots of useful things there. Anyway, back to what's on the board. Cool. So let's look at what else we have over here. Let's go with the distance. So that distance one's a great question. So I like this question. Find the distance from the point 3, 7, 5 to all the planes and all the axes, essentially. So we'll look at a few of these. So I want to find the distance to the plane, sure, to the XY plane. So there's actually a really easy way to do this question. If we think about, in fact, let me ask a different question first. So off to the side here, what if I wanted to find in 2 dimensions the distance from the point 3, 4 to the x-axis? Let's draw it. So over 3, up 4. So there's the point right there, 3, 4. And if I want to find the distance to the x-axis, there's a lot of different distances we could consider, but there's only one right one. It's not that distance. It's not that distance. It's the shortest distance or the perpendicular distance. Right? So if we drop a perpendicular from our point to our axis, that's the distance we're trying to find, which is, I think, pretty straightforward because we know that this point here is going to be the point. What point? Yeah. And if only one of your coordinates is changing, the amount of change is the distance you have traveled. So here you can easily say the distance is 4. Because from 3, 0 to 3, 4, the distance is going to be 4. You can also do the math, right? You could use the distance equation or formula and say it's the square root of, it's going to feel a little silly, 3 minus 3 squared plus 4 minus 0 squared. Let's see, that's the square root of 0 plus 16, which is just 4. So the math definitely works if you want to do it the longer way. But specifically, if only one coordinate is different and everything else is the same, sorry, back that up. If only one coordinate's the same and everything else, now I just need to draw it, sorry. I was about to say something that was going to be smart and then I screwed it up. So let's draw a picture. So our point here is over, it's 3 in the x direction, 5 in the y direction, and 7 in the z direction. So here's our point 3, 7, 5. And if I drop this back down to the xy plane, well, now that's the point 3, 7, 0. So yes, what I was saying was correct. I just got it backwards in my head. So if only one coordinate's changing, that change is the distance. This distance here is exactly going to be a distance of 5. And again, we could use the distance formula, right? We could say, okay, great. Between this point and that point, the distance is going to be the square root of 3 minus 3 squared plus 7 minus 7 squared plus 5 minus 5 squared. But if, 5 minus 0 squared, got a little carried away there, which is definitely going to be 5. So the distance from any point to a particular plane is just whatever coordinate it's not. So if it's the xy plane, it's the z coordinate. If it's the yz plane, it's the x coordinate, and so on. What if it was from the point 3, 7, 3, 7, negative 4? Then what would the distance be? It would be positive 4, right? Distance is always positive, or I should say non-negative. So it's the difference in your coordinates, which should be always thought of as a positive number. Going to an axis is a little bit different. So if I want to go to, say, the x-axis, well, then I'm looking at that distance there. But really, I'm just thinking about the point on the axis I need to kind of find the distance to. So just like when we dropped down to the xy plane, the z coordinate became 0 and every other coordinate remained the same. If we go over to the x-axis, well, on the x-axis, the z coordinate and the y coordinate both have to be 0. That's kind of the definition of being on the x-axis. And so on this axis over here, the only coordinate that isn't 0 is the x coordinate. And it remains the same, right? We didn't move away from that x coordinate of 3. So then to find the distance between our point and the x-axis, it's going to be, again, the square root of 3 minus 3 squared plus 7 minus 0 squared plus 5 minus 0 squared. And that's going to be the square root of 49 plus 25, which is the square root of 74. But really, the thing you need to keep in mind here is that when if you're going to a plane, you're just letting the coordinate that's not in the name of the plane becomes 0. If you're going to an axis, you're letting the two coordinates that are not the name of that axis become 0. But it's easier to think of if you draw a picture, right? Definitely drawing the picture here made it easier to be like, oh yeah, x is 3 and y and 0 is 0, both 0 here. Or over here, x is 3 and y is 7 and the z coordinate's 5. Or I mean 0. Apologies. So I think drawing a picture for these is a good idea. Questions about that? All right. We'll get to that last one up there, but I think we should talk a little more about vectors just in general before we talk about that one. But maybe not. Maybe not too much. Let me do this here. Yeah. I'm going to skip the other 4 there because I think they're pretty much the same. Sorry. There we go. Cool. More on vectors. Yeah, let's see here. So drawing vectors. Yeah, there's lots to say about vectors. So if I wanted to say draw the vector, I like writing this way, 2, 3. You typically, although you do not have to, but you're typically starting at the origin and then just going that much in the first coordinates, how much you're moving in the x direction, the second coordinates, how much you're moving in the y direction. So over 2, up 3. And then you have the initial point at the origin and the terminal point at your point 2, 3. So this is my vector 2, 3, or 2, 3. The magnitude of the vector, also known as the length of the vector. And we find it in the usual way, really just meaning using the distance formula, right? You could think of the magnitude of v as being the distance between the initial point and the terminal point, which is why we like to think of them starting at the origin, because then if you're using the distance formula, it's just going to equal the square root of, you don't really need to write the zeros here, 2 minus 0 squared plus 3 minus 0 squared, which is just the square root of the sum of the squares of the components of the vector. So this vector has a magnitude of the square root of 13. We talk less about the direction of a vector, but you could say that if you want to, you can talk about the angle that this vector makes with the x-axis. So if we want to talk about the angle / direction, well, we could say that we know that for this vector, tangent of that angle is equal to the opposite over the adjacent, which is going to be 3 over 2. So we could say that our direction or our angle is the arc tangent of 3 over 2. But we don't really talk about that a whole lot. Sure. What else? Yeah. Just a few other things. So we can find the vector that, what's the word I'm looking for? Begins, why use fancy words? That begins at point A, which is the point 2, 1, and terminates at point B, which is the point 6, -1. We don't need to draw a picture here, but we certainly can. So it's starting at the point 2, 1, and ending at the point 6, -1. So our vector looks like this. And the arrow points towards B. And we could write the vector as the vector AB with an arrow above it. And we find the coordinates just by taking the coordinates of the terminal point and subtracting the coordinates of the initial point. So we could write it as 6 - 2 for the first coordinate and -1 -1 the second coordinate, which is going to end up being 4 comma -2, which seems reasonable, right? We went over 4 and down 2. A lot of the things about vectors work as you would expect them to, which is nice. Why don't you all find the magnitude of AB, of vector AB? I'll give you a minute. A minute seems too long. That is the magnitude of the vector AB. Square root of 20 or simplified 2 root 5. There was something I wanted to say here that actually was. Oh, I should also point out, I will mostly draw two-dimensional examples because it is easier to draw them, see them. But I should say, and I will say, try to say frequently, this concept is certainly applicable or analogous to a three-dimensional version. So like if I gave you two coordinates in 3 dimensions, you could find the vector that began at 1 and the other by subtracting the terminal point minus the initial point to get the coordinates of the vector. So all these ideas in 2 dimensions have 3D analogs. We will do examples of them sometimes, but again, it's easier for me to draw and for you to see my drawings if they are 2-dimensional typically. Yes. There might be even more. Yes, so there are certainly vectors that in higher dimensions, that you can have a vector in 4 dimensions, 5 dimensions, 6 dimensions. As far as like physical dimensional space, we talk about having 2-dimensional or 3-dimensional vectors. Higher dimension vectors, like you can use a higher dimensional vector to describe some other quality about a thing sometimes, but yeah, visualizing those people, I think people are liars. People say they can visualize these 4th dimensional, 5-dimensional shapes. I'm like, okay, if you say so. But as far as like actual physical objects, we typically limit ourselves to 2 and 3-dimensional vectors, although it's certainly there are things we will talk about how some concepts like the dot product and other things have analogs in 4 or 5 or higher dimensions. So yes, there are certainly higher dimensional vector spaces. We just don't talk about them a lot in this class. Certainly, I imagine most of you probably won't take linear algebra math 22A, but if you did, that's where you would talk more about vectors in higher dimensions. It's a good class, but probably not required for most of you. So then actually what I wanted to do here is and this is something we do often, find a unit vector. What do I mean by that? We'll say it in a second. In the same direction as the vector AB. So by unit vector, we mean a vector of length 1. And often we want, so really a lot of the reason we want to find unit vectors is because sometimes someone's going to ask you all, what direction is this vector pointing in? And technically there's an infinite number of correct answers. I might say the vector, let me just write something over here. Right, I might say the vector is the vector 1, 2. You might say the vector is the vector 2, 4. Someone else might say 3, 6, or 5, 10, or 100, 200. And all those vectors point in the same direction. So to limit the number of potential correct answers, we often say, tell me the unit vector that points in the correct direction, because then there's only one right answer. So often that when we ask for like the direction of a vector, what is implied or sometimes explicitly said is as a unit vector. So it's a good idea to, when you're asked to find the direction of something, to write your answer as a unit vector, which we do by taking the original vector and dividing it by its own magnitude. So the unit vector here, which we often write as the lowercase u with an arrow above it for u for unit, is going to be the vector AB divided by its own magnitude. In this case, it's going to be the vector 4 comma negative 2 divided by 2 root 5. That's a perfectly fine way of writing your answer. You might prefer to write it as each component divided by 2 root 5. So you have like 4 over 2 root 5, comma negative 2 over 2 root 5. We don't typically rationalize our denominators here. I don't know why, other than people are just lazy, but we usually don't. You could simplify this as 2 over root 5, comma negative 1 over root 5. And if you really, really wanted to, you could write it as 2 root 5 over 5, comma negative root 5 over 5. They're all the same. Any one of those answers is perfectly correct. But the point about all of these answers is all of these answers have a magnitude of 1. Let's check. Let's check up here. We have room down here. Sure, I've studied this piece of paper over here already. So just to point out, if you pick any one of these vectors, I'm going to pick that one because it looks the easiest. The magnitude of this vector u is going to be the square root of 2 over root 5 squared plus negative 1 over root 5 squared. That's going to be the square root of 4/5 plus 1/5, which, hey, wouldn't you know it, that's the square root of 1, which is 1. Should be no surprise there, because we already knew it was going to have a length of 1. Yeah, this is a great time to say that. So here's a fun trick for doing this. This is something I would highly recommend you remember. Let's say someone asks, so another way to phrase this instead of saying find the unit vector in the same direction as this vector, we might use the language of, say, normalize the vector. I'm going to pick something awful. Sure, the vector 3 over 1027, comma, sure, 5 over 1027. And again, normalize just means find a unit vector in the same direction as. The given vector. Okay, here's the fun trick. If you're trying to find a vector in the same direction, a unit vector in the same direction as the given vector, well, you know what? This vector I've given you is really terrible. It's also really small, right? It has a length that is much, much less than 1. So let me draw it here, or pretend to draw it. It's over 3 1027s and up 5 1027s. So let's pretend that's my vector there. Let's call it V. And instead of finding the unit vector or the magnitude of that, which is going to suck, and then dividing by that, find another vector that points in the same direction first. You can multiply this by literally anything you want. Like I can multiply it by 1027. And I'm going to call that W. And W is the vector that's 1027 times V, which is going to be 3 comma 5. And both of those vectors point in the same direction. So if you take either one of them, I wonder which one I'm going to pick, and divide by its own magnitude, that'll give you a unit vector that points in the right direction. So if you're trying to normalize a vector that's terrible, you can make it less terrible by multiplying it by any non-zero number you want. True story. So in this case, we should normalize W equal to 3 comma 5. So then our vector U is going to be the vector W divided by its own magnitude, which is the square root of 9 plus 25. You can write it like this, or you can write it as 3 over root 34, comma 5 over root 34. Much, much nicer than doing 3 over 1027 divided by the square root of 3 over 1027 squared plus 5 over 1000, right? It's awful, just terrible. So make your life easier. If you ever have to normalize something, pick a multiple of your thing to make it easier to deal with. Cool. All right. Moving along. Vector addition and subtraction. What I really want to say is that vector addition and subtraction works how you would hope it will work. Meaning, if you add two vectors together, you're just going to add their components together. If you subtract two vectors together, you're just going to subtract their components together. So for example, if I was trying to add the vectors, say u equal to 3 comma 1 and v equal to 2 comma 5, well, the resulting vector u plus v is just going to be 3 plus 2 comma 1 plus 5, which is going to be the vector 5 comma 6. Graphically, there is a very nice way that vectors add together graphically. So if I draw the vector 3 comma 2, sorry, 3 comma 1, so over 3 up 1, there's my vector u. I draw the vector v over 2 up 5. Again, both of them starting from the origin. There's my vector v. And then if I want to add v to u or u to v, it doesn't matter which order I do it in because vector addition is commutative, right? Either order doesn't matter. I'm just going to take v here and essentially slide it over so that its tail is on the head of u. So I'm just going to go like that. Essentially, I'm going to start here and then go over 2 and up 5. Or I go the other way. I can start here and go in the direction of u. Over 3 and up 1. And then this resulting vector, that is your vector u plus v. And it's not surprisingly the vector that starts at the origin and ends at the point 5 comma 6. So vector addition, vector subtraction is pretty straightforward as long as you're given vectors that are, I mean, there's really, I can't think of what to say about it. Like you've got vectors in the, I guess you could be given vectors in a less typical format, although really, these are the way we write vectors. So for another example, let's say I was given the vectors v equal to 3 comma 1 comma 2 and u, gosh, my v's and my u should look different. U equal to -1 comma 0 comma 4. And I want to find 2u plus 3v. So when you multiply a vector by a scalar, you just get to multiply each component by that number. So that's just going to be 2 times the vector -1, 0, 4. That's a 4, not a u. Plus 3 times the vector 3, 1, 2. And then you essentially distribute the 2 to each component and distribute the 3 to each component. So you get the vector -2, 0, 8 plus the vector 9, 3, 6. You add all the components together. -2 plus 9 is 7. 0 plus 3 is 3. 8 plus 6 is 14. And there is your resulting vector. There's not a lot to it, really, as far as adding and subtracting vectors goes. You add them the way you want to add them. You subtract them the way you want to add them. You multiply them by scalars the way you would think you'd multiply them by scalars. Questions about that? Oh yeah, let's do. Sure, I should do one more graphical thing. So let me do one more thing with these two vectors here. What if I actually? I think I can just draw it right here. What if I wanted to draw u minus v? So I want to go in the u direction, and then instead of going in the v direction, I want to go in the opposite of the v direction. So I can think of that really as u plus -v. So I'm going to go in the u direction instead of going in the v direction, I end up going in the -v direction. So I'm going to go not in the 2 over and 5 up, but in the 2 left and 5 down. So from the point 3 comma 1, I'm going to go 2 left and 5 down. So there's u minus v. So here's my resulting vector. Again, mathematically, we can just do the math and say, well, u minus v is going to be 3 comma 1 minus 2 comma 5, which is going to give me 3 minus 2, comma 1 minus 5, which looks like what we've got, right? It looks like we've gone over 1 and down 4 from the origin. What I want to point out here is there's kind of a what always feels to me like a tricky way of just drawing u and v and then getting u minus v, and I never can remember which way to do it until I've done it the long way. So if you just start by drawing u and v starting at the origin, if you want to do u minus v, you essentially start at the head of v and draw the vector in the direction of the head of u, and that's the same vector. That is also u minus v. But I literally can never remember which way you do it. Like if you start here and go there, or start here and go there until I've actually done it the long way. So I don't know if that's necessary or important to remember, but there it is. Let's see. Are we there yet? We're almost there. Let's look at this one. Suppose, okay, we got a 3D question. Suppose V is a 3D vector in the first octant with a length of 3 that makes an angle of 60 degrees with the x-axis and an angle of 45 degrees with the y-axis. Okay, write V in terms of, that's a good question. Write V in terms of its components. 3D vector. Okay, sure. Maybe. I don't know. This might require too much thinking. So we've got a vector, and we know it's making a 60-degree angle with the x-axis. I hate drawing in 3 dimensions. Okay. Okay, we're gonna pretend like this doesn't look terrible. So, so what we're saying here is this angle it's making with the x-axis is 60 degrees, and this other angle it's making with the y-axis. I feel like it's not drawn well. Like, sorry, it's 45 degrees. What? So, let me do this. Here, this will make it easier. So if you drop down this point there, it lies somewhere in the XY plane. So like it's kind of like this here, that there. Right. So that, yeah. How do we do this? It's a good question. I don't know if I have a good answer. Yeah. Anyone have any thoughts? You guys like that's what we wrote on the board. We thought you would know what to do. In terms of its components, so taking a 60-degree angle with the x-axis. What section is this from? Or is it from a section? Like, so one of you wrote it on the board. Right. Oh, okay. All right. Let's start off with something easier, and then we'll see if we can back up to this. So let's say we were just given the following. Let's say that we have a vector. Not gonna, yeah. Okay, sure. Let's start off with a 2-dimensional example to kind of wrap our heads around it. So let's say that we are given a vector. Oh, and I did forget to mention there was a length of 3 here. Let's write that in before I forget. Let's say that we're given a vector of length 4, and it's making a 30-degree angle with the x-axis. And we want to find its components. So at least in this example, I'm just thinking trigonometry. So I'm trying to find essentially the x and the y components. So I know that sine of 30 degrees is equal to the opposite divided by the hypotenuse. So my y component is just going to be 4 times sine of 30 degrees. And sine of 30 degrees is 1/2. That's going to be 2. Similarly, cosine of 30 degrees should equal the adjacent divided by the hypotenuse, which is going to give me that x is equal to 4 times cosine of 30 degrees. And if we know that sine of 30 degrees is 1/2, we know that cosine of 30 degrees has to be the square root of 3/2. Because those two numbers always go together when you're talking about trig functions of angles. So we end up getting 2√3. So here, our vector, which I didn't give a name to, let's call it v. Our vector v is equal to the vector with components. This is the x component, and that's the y component. Okay. All right. So now back to this other problem that seems a lot harder. So let's label some things. We know that we're going to call essentially our vector, we're going to call it x, y, z. It's going to have 3 components. So this length is the x length. This length is the y length. This length is the z length. I guess we could draw it up here too. Yeah. Okay. Maybe. I don't know. Let's call this L for a second. Just kind of making shit up. Here's one thing I know for sure. X squared plus y squared plus z squared has to equal 3 squared. You can either think of that kind of in the Pythagorean theorem sort of way, or you can think of it in the magnitude of the vector kind of way, right? The magnitude of my vector is the square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared, and it should equal the length of the vector, which was given to us as 3. And then I square both sides. And then what? Yeah. The trouble I'm having with this is thinking about like, yeah, I'm really kind of three-dimensional visualization is not my forte, unfortunately. I'm trying to think about kind of like what this triangle is doing here, like with this triangle here. Don't love it. Okay, here's what I want to do. I want to try to drop a perpendicular to the y-axis. Yeah, okay, that seems smart. So let's see if we can do this. So just think about the y-axis here and my vector coming up that way and going like that. Okay, this might work. So then if we drop a perpendicular from here to there, that is perpendicular. Oh my gosh, maybe to my axis there. Sorry if this looks terrible. So I'm thinking of this is my y-axis. This is my vector. And like here's my z-axis and my x-axis. Yeah. And so what we're saying here is that in this triangle, this angle had better be 45 degrees. And I don't love what I've said here. Gosh, I cannot see this. It is just like, yeah, because I don't like it. Sorry. I'm just like, yeah. Suggestions? Sure. Let me take a look. Because I wrote what I remember now. Okay. Sure. So we've got that triangle. Yeah. I'm a little bit stumped. Even looking at this, it still feels like it doesn't make a whole lot of sense. So I definitely I'm sorry that you are all watching me meander through this problem. Let's see if we can make it make a little more sense. So here's what's written over here that I don't know if I exactly agree with, but we'll write it down anyway. So what's written down here is that we have a 60-degree angle here. This is the vector. Okay, fair enough. And this is the x-axis. And this here is written as the square root of y squared plus, okay, of course. That makes sense as I'm writing it there. It's just visualizing it being so this triangle here, okay, I'm gonna try and draw it. Pray. So this is x, that's x. This side here, that's my square root of y squared plus z squared. And then this other side here is obviously the vector. Right. That, and yeah, but man. So yes, so that is a right angle there. It's being made. Yeah, okay, I buy it. Cool. So this triangle is that triangle there. Seem plausible? I think I finally got my eyes to believe what I'm saying. And then in a similar way, we can draw the other one that I was trying to draw before. Let me draw it this way. So for this 45-degree angle here, this side is still the vector. And then this side is going to be the y-axis. And then this line I was trying to drop down here, that is your square root of, well, see, I'm on the y-axis, so it's better be the square root of x squared plus z squared. Yeah, yeah, okay, good. Matches, all right, good. Okay. Anyone have thoughts, questions, comments about that before we try to figure this thing out? Be like, James, you're doing it wrong. I don't think I'm doing it wrong. I think we've got this handled. Okay. Okay, so we know that the length of this is 3. And now I think we just have a bunch of equations we have to deal with. So I can think of a couple of equations. So here's what I don't want to write. Or I guess I'm going to write. All right, we already have this equation, which is certainly true for both of these triangles, right? If you use the Pythagorean theorem for this triangle or that triangle, you'll get the same equation. So there's no need to do that. And then we have some trigonometry. We have that sine of 60 degrees. Do I want to use sine? I don't know, maybe. I'm just gonna write down all the things. Sine of 60 degrees is equal to 1/2. Nope, it's not. It's equal to the square root of 3/2. And it's also equal to the opposite over the hypotenuse. Square root of y squared plus z squared all over 3. I know that cosine of 60 degrees is equal to 1/2. And that's equal to x divided by 3. Hey, that's helpful. I just found x. So that means x has to equal 3/2. Sweet. I can probably do a similar thing here. If I do cosine of 45 degrees, that's going to equal the adjacent over the hypotenuse. But we also know it's equal to the square root of 2/2. That means y is going to equal 3√2/2. And then we can use this equation to find z. So we can say that x squared plus y squared plus z squared equals 9. So then 9/4 plus 9 times 2 is 18/4 plus z squared equals 9. So z squared equals 9 is 36/4 minus 18/4 minus 9/4. 36 minus 18 minus 9 is also 9/4. So it looks like z is also going to be the square root of, is going to be 3/2. The square root of 9/4. Yeah, I can do it. Cool. That was only a little terrible. Yeah. Yeah, it was not easy to draw. But a good question. Just not my favorite. Oh, it's 2 o'clock. Well, time flies when you're stuck on a math problem. All right. I'll see you all Monday. Have a lovely weekend. Sorry we didn't get through more there. Apologies for getting stuck. But still, we did it. We'll talk about the dot product next week for sure. I have office hours as usual. That's all I got.